There is a paste that costs $2. Apply it to 4 specific contact points during a brake job, and it eliminates brake squeal permanently. Not temporarily, not until the next rain, not until the pads bed in. Permanently. The same brakes that squealed every morning for 6 months after your last $250 brake job will never squeal again. The global brake service industry generates over $20 billion annually in the United States. Brake noise complaints, squealing, grinding, and rattling are among the top 5 reasons customers return to a shop after a brake service. A brake noise comeback generates another service visit, another diagnostic fee, and often another set of pads installed to replace the pads that were installed 6 months ago. This comeback cycle is not an accident of brake system complexity. It is the predictable consequence of a standard brake installation procedure that skips the one step that prevents brake noise permanently. That step takes 3 minutes. The material costs $2. Every Formula One team does it. Every aircraft maintenance facility does it. Every military vehicle depot does it. The average independent auto shop does not do it. And the average dealership service department does not do it because the brake noise complaint it prevents is a service revenue opportunity they prefer to keep open. The material is copper anti-seize compound, not brake-specific grease, not caliper slide pin lubricant, not the little packet of brake lubricant that comes in the brake pad box. Copper anti-seize, the gray paste with copper particles sold at every auto parts store for $2. Applied to the brake pad backing plates, the caliper slide pins, and the caliper bracket contact points during installation. This is the story of copper anti-seize and brake noise, the installation step that racing engineers standardized 60 years ago, that the auto service industry skips to generate comeback visits. And that takes less time to explain than the average brake noise diagnosis. Let me take you back to where this begins, to an aircraft maintenance hangar at Edwards Air Force Base, California, in 1952. The United States Air Force was conducting accelerated testing of high-performance aircraft brake systems for the new generation of jet aircraft entering service. Jet aircraft landing speeds were dramatically higher than propeller-driven predecessors, creating brake heat loads that exceeded anything previously encountered in aviation maintenance. At these temperatures, brake disc temperatures reached 1,200 degrees Fahrenheit during maximum effort stops. Conventional brake hardware lubricants vaporized, seized, and failed. Caliper slide pins that were lubricated with standard grease at installation would be dry and seized within 50 landing cycles. Seized slide pins caused uneven pad wear, brake drag, and the vibration-induced noise that is the acoustic signature of a brake system in mechanical distress. Air Force maintenance engineers testing alternative lubricants at these extreme temperatures discovered that copper-based anti-seize compounds, formulations of copper powder suspended in a petroleum or synthetic grease carrier, remained functional at temperatures that vaporized standard lubricants. Copper's melting point of 1,285 degrees Fahrenheit meant that the copper particles in anti-seize compound remained solid and lubricating at brake temperatures that consumed every other available lubricant. The copper particles compressed between metal surfaces under load provided a soft metal lubrication mechanism. The copper deformed plastically to fill microscopic surface irregularities and maintain a lubricant film under conditions that would strip away any fluid lubricant. The aviation maintenance community standardized copper anti-seize for brake hardware lubrication across military and commercial aircraft by the late 1950s. Boeing, Douglas, and Lockheed aircraft maintenance manuals from this period specifically called out copper anti-seize as the required lubricant for brake caliper hardware, slide pins, and backing plate contact surfaces. These specifications have not changed in 60 years. Current Boeing 737 and 777 maintenance documentation still specifies copper anti-seize for brake hardware. When an airline that operates on margins measured in fractions of a cent per seat mile standardizes a maintenance practice, it is because that practice is the most cost-effective option available. Motorsport discovered copper anti-seize brake application through the shared engineering culture between military aviation and early motor racing in the 1950s and 1960s. Formula One teams of the 1960s, operating at the frontier of brake system development with disc brakes that generated temperatures comparable to military aircraft, adopted copper anti-seize for brake hardware as standard practice. Team engineering notes from Ferrari, Lotus, and BRM from the mid-1960s, preserved in Motorsport Archive collections, document copper anti-seize application protocols for brake caliper preparation. The practice has remained unbroken in professional motorsport from the 1960s to the present. Every Formula One car racing this weekend will have copper anti-seize on its brake caliper slide pins and backing plate contact points. Your commuter car did not receive the same treatment at its last brake service. Now let me show you exactly why brake squeal happens, and why copper anti-seize eliminates it while other lubricants fail. Brake squeal is a resonance phenomenon. When a brake pad contacts a rotating rotor, the friction force between the pad and rotor can excite vibration modes in the brake pad assembly at frequencies in the audible range, typically between 1,000 and 16,000 Hz. Whether these vibrations produce audible squealing depends on whether the excitation frequency matches a natural resonance frequency of the brake pad and caliper assembly, a condition called stick-slip resonance. The physics of stick-slip resonance follows a brutal sequence. As the pad contacts the rotor, static friction initially holds the pad stationary relative to the rotor surface. The rotor's motion deflects the pad elastically until the elastic restoring force exceeds the static friction force. The pad then slips suddenly, releasing the stored elastic energy. It re-engages the rotor, stores elastic energy again, and slips again. This stick-slip cycle, occurring thousands of times per second at the contact interface, is the source of the vibration that produces squealing when its frequency matches a structural resonance of the brake assembly. The critical factor controlling stick-slip resonance is the ratio of static friction to kinetic friction at the pad contact interfaces. Not just the pad-to-rotor interface, but all the contact interfaces in the brake assembly. High static to kinetic friction ratios, which occur when metal contact surfaces are dry and corroded, promote aggressive stick-slip behavior that excites resonance more easily. Low static to kinetic friction ratios, which occur when contact surfaces are properly lubricated, reduce stick-slip excitation below the threshold needed to sustain resonance. The brake assembly has several metal-to-metal contact interfaces beyond the pad-to-rotor interface. The brake pad backing plate contacts the caliper bracket at its edges and ears. These contacts transmit the braking force from the pad to the caliper and must slide freely as the pad wears. The caliper slides on pins or bushings that allow it to move perpendicular to the rotor to maintain even pad contact as the rotor wears. These contact interfaces, backing plate to bracket and caliper to slide pins, are the primary locations where improper lubrication allows corrosion and high friction ratios to develop, creating the mechanical conditions for stick-slip resonance. Conventional brake-specific greases address these interfaces adequately when new, but they fail progressively over time for two reasons. First, they are water-soluble or water-dispersible. Brake systems are exposed to rain, road spray, and car washing, which progressively wash standard grease from the contact interfaces. Second, they are temperature-limited. The thermal cycling of normal brake use progressively oxidizes and hardens standard greases, reducing their lubricating effectiveness. Copper anti-seize is neither water-soluble nor temperature-limited at brake operating temperatures. The copper particles that provide the lubrication are metallic. They do not oxidize at brake temperatures, do not dissolve in water, and do not wash from the contact surfaces under normal exposure. A single application of copper anti-seize at installation maintains effective lubrication of the contact interfaces for the life of the brake pad set. A study published in the SAE Technical Paper Series in 2019 measured stick-slip friction behavior at brake pad backing plate, contact interfaces lubricated with copper anti-seize, standard brake grease, ceramic brake lubricant, and dry, unlubricated conditions across 50,000 thermal cycles, equivalent to approximately 30,000 miles of typical driving. Copper anti-seize showed static to kinetic friction ratios of 1.05 to 1.12 across all 50,000 cycles. That is the range associated with squeal-free brake performance. Standard brake grease showed ratios of 1.08 at installation, increasing to 1.31 after 10,000 cycles and 1.47 after 30,000 cycles, well into the range associated with squeal-prone brake systems. Ceramic brake lubricant showed a similar progressive increase, reaching 1.39 after 30,000 cycles. Dry unlubricated contact showed ratios of 1.5, 2 to 1.7, 1 throughout, the most squeal-prone condition of all. Copper anti-seize maintained squeal-preventing friction characteristics for the entire test duration. Every other lubricant degraded into the squeal-prone range within the equivalent of a single set of brake pads. And this is where the story takes a dark turn. The automotive brake service industry's revenue model includes a specific and predictable revenue stream called the brake noise comeback. A brake noise comeback occurs when a customer returns to the shop because their brakes are squealing after a recent brake service. Industry service data shows that approximately 20 to 30% of brake jobs generate a noise-related comeback within the first 12 months. Each comeback generates a diagnostic fee of $50 to $100 and frequently results in pad replacement at full labor cost to address the noise complaint. For a shop performing 500 brake jobs per year, the comeback revenue can represent $25,000 to $50,000 in additional annual billing. The standard brake installation procedure taught in automotive trade schools and published in manufacturer service manuals specifies the use of brake-specific lubricant, the little foil packet that comes in the brake pad box, on caliper slide pins and backing plate contact points. This lubricant is adequate for preventing noise during the initial break-in period. It is not adequate for preventing noise over the full service life of the brake pad set. The training and the specification both produce a procedure that results in acceptable initial performance and predictable noise comeback within 12 to 24 months. Copper anti-seize is not mentioned in standard brake installation procedures published by any major brake pad manufacturer. It is not included in the hardware kits sold with brake pad sets. It is not recommended in automotive service textbooks used in trade school curricula. It is not discussed in automotive service advisor training materials. It is available at every auto parts store, costs $2, and is used by every professional race team and every aircraft maintenance facility that installs brake hardware. Its absence from consumer automotive maintenance guidance is not an oversight. It is the maintenance of a product knowledge gap that sustains a predictable and profitable service comeback cycle. The brake pad manufacturer's complicity in this gap is structural. A brake pad set that never squeals and never generates a noise comeback is a brake pad set whose performance does not create an incentive to try a different brand next time. Brake noise is the primary driver of brand switching in the brake pad market. Consumers who experience noise with brand A switch to brand B. Brand B's premium noise-free formulation commands a higher price. That premium price is not justified by the pad formulation. It is justified by the proper installation procedure that the premium brake job includes. A $2 tube of copper anti-seize applied during installation of the cheapest brake pads available produces better noise performance than premium pads installed without it. The brake pad industry's pricing structure depends on consumers not knowing this, but the knowledge survived. It survived in the racing paddocks, in the hangars, and in the garages of people who install their own brakes. The Formula One brake preparation process has been documented extensively through the sport's growing media access to team operations. Behind-the-scenes footage and technical articles published by teams and by motorsport media consistently show copper anti-seize being applied to brake caliper slide pins and pad contact points during wheel and brake changes. This is not a trade secret in professional motorsport. It is visible standard practice that anyone watching race preparation footage can observe. The knowledge that Formula One uses copper anti-seize exists publicly. It simply has not been connected to the commuter car brake service in any consumer-facing automotive publication. Commercial aviation's continued specification of copper anti-seize for brake hardware is documented in publicly accessible maintenance manuals. The Boeing 737 Aircraft Maintenance Manual Task 324100 brake assembly installation specifies copper anti-seize compound for brake caliper bolt threads and contact surface. This document is publicly accessible through the FAA's regulatory document portal. The maintenance procedure that keeps commercial airline brakes silent and functional through thousands of landing cycles is documented in a public government database. It is simply not a document that automotive consumers have been directed toward. The DIY brake service community has been the primary popularizer of copper anti-seize for consumer brake jobs over the last 15 years. YouTube channels dedicated to automotive DIY consistently recommend copper anti-seize as part of proper brake installation, citing their own experience of zero brake noise comebacks on vehicles where they use the compound versus recurring noise on vehicles where they use standard brake grease. The combined view count of DIY brake installation videos recommending copper anti-seize runs into the tens of millions. The automotive service industry's formal training and documentation have not acknowledged this community-generated best practice. A fleet maintenance manager for a regional delivery company documented his company's transition from standard brake grease to copper anti-seize for all brake hardware on a fleet of 140 delivery vans in a 2020 maintenance report shared at a fleet management conference. Before the transition, brake noise-related service calls averaged 23 per month across the fleet. In the 12 months following the fleet-wide adoption of copper anti-seize, brake noise-related service calls averaged 2 per month, a 91% reduction in brake noise, complaints from a single $2 change in installation procedure. The fleet manager's report recommended the practice to every fleet operator in attendance. It has not been adopted in any standard automotive service curriculum. Here is exactly what to do. 4 contact points, 3 minutes, no more brake noise, materials needed, copper anti-seize paste. Available at any auto parts store under brands, including Permatex, Loctite, and CRC. A standard 8-ounce tube costs $6 to $10 and contains enough material for approximately 20 brake jobs. Per brake job, material cost is 0.30 to 0.50. Do not substitute nickel anti-seize or silver anti-seize. The parts that can contaminate brake friction surfaces and reduce braking effectiveness. Copper anti-seize specifically is the correct compound for brake applications. You also need a clean rag or paper towel for cleaning contact surfaces before application, and brake cleaner spray for removing old grease, rust, and contamination from contact surfaces. The 4 contact points. Point 1. Caliper slide pins. These are the 2 pins, typically 10 to 14 millimeter bolts, that the caliper slides on as the pads wear. Remove each slide pin. Clean the pin and its bore with brake cleaner. Apply a thin coat of copper anti-seize to the pin shaft and reinstall. The pin should slide smoothly in its bore with no binding. Point 2. Brake pad backing plate ears. These are the tabs at each end of the brake pad that contact the caliper bracket. Clean the contact areas on both the pad ears and the caliper bracket with brake cleaner. Apply a thin smear of copper anti-seize to the bracket contact surfaces, not to the pad itself. The copper anti-seize should be on the metal bracket where the pad ears slide, not on the friction material. Point 3. Caliper bracket abutment surfaces. These are the machined surfaces on the caliper bracket where the backs of the brake pads rest. Clean thoroughly and apply a thin coat of copper anti-seize. These surfaces need to allow the pad to move freely inward as it wears. Any binding here creates uneven wear and noise. Point 4. Brake pad backing plate center area. Apply a thin smear of copper anti-seize to the flat back surface of each brake pad backing plate. The metal back, not the friction material side. This prevents the metallic resonance between the pad backing plate and the caliper piston or caliper fingers that is a secondary source of brake squeal. Critical cautions. Never apply copper anti-seize to brake friction material, the friction surface of the pad, or the rotor surface. Contamination of friction surfaces dramatically reduces braking effectiveness and creates a safety hazard. Apply copper anti-seize only to the metal contact points described above. Use it sparingly. A thin film is effective. Excess copper anti-seize that squeezes out onto friction surfaces during brake application must be cleaned off with brake cleaner before driving. Now look at the cost comparison. Brake noise diagnosis and pad replacement at a shop costs $150 to $300 per axle. Premium noise-free brake pad sets, such as Akabono Pro Act, cost $60 to $120 per axle. That premium price is driven primarily by installation procedure, not by friction material. A standard brake pad set plus copper anti-seize costs $25 to $45 per axle in pads, plus 0.30 in copper anti-seize. Zero brake noise for the life of the pad set. And before this closes, think carefully about what brake squeal is actually telling you. Every time your brakes squeal, a stick-slip resonance cycle is occurring thousands of times per second at a metal contact interface inside your brake assembly. The noise is energy, mechanical vibration energy, being dissipated as sound rather than as heat through the friction material. The vibration that produces that sound is also fatiguing the brake hardware, the caliper pins, the bracket, and the pad ears at a microscopic level with every braking event. A brake assembly that squeals is a brake assembly that is working harder than it needs to and wearing faster than it should. The solution to this has been known since 1952. It has been standard practice in commercial aviation for 60 years. It has been standard practice in Formula One for 60 years. It costs 30 cents per brake job. The $20 billion brake service industry generates a portion of its revenue from brake noise complaints that this 30-cent application prevents. Brake pad manufacturers generate premium pricing from noise-free formulations that properly installed standard pads can already match. The automotive training curriculum produces mechanics who follow procedures that reliably generate noise comebacks within 12 months. Every element of the system is aligned around maintaining the brake noise complaint as a recurring revenue event, rather than eliminating it as a solved engineering problem. But it is solved. It has been solved since the Air Force engineers at Edwards discovered that copper does not vaporize at brake temperatures. The solution is sitting in an $8 tube at the auto parts store. The instruction to use it was simply never included in the procedure that generates the $20 billion. Some knowledge never truly disappears. It waits in a Boeing 737 maintenance manual, in a Formula One team's brake preparation procedure, in an $8 tube on the auto parts store shelf next to the brake grease packet that comes in the pad box. For the driver who asks why the racing engineer does something different from the service advisor and decides to do what the racing engineer does, the silence begins there. If you are tired of paying for the same noise twice, remember this: the fix was never expensive. It was never complicated. It was only kept out of the procedure.